the short run model, and then you also can get what we call as the ECM term that provide it measures how fast the system return to equilibrium after it decays. For example, so this one is the long run coefficient. So meaning that this is the long run relationship. The distance between these two series represent the long run relationship, the long run relationship between the variables. So if they say certain part of this data, so it suddenly deviate from the distance. Let's say the distance between them represent the long-term relationship. But let's say certain part of the series it is slightly deviate from that distance from the average of the distance, so that we can estimate the ECM and then get the error correction term. Okay. So the ECM is given by this equation, and then the P, this one already updated the action notes. So the parameter of this, okay, provide an estimate of speed of adjustment of the short run deviation to long run equilibrium. We decide how quickly the equilibrium will be restored. So phi must be between -1 and 0 for meaningful interpretation. So if you select this one, I got the result. Then if you estimate that one, okay, the coefficient for the ECM error correction term -0.55. Yeah. So in terms of interpretation, you see that estimated coefficient for the equilibrium error term is -0.055, -0.5545. It implies that about 55%, 55.46% of any disequilibrium between the two series is corrected within 1 period. Okay, so got this data in data, so meaning within 1 year, it will correct about 55% of the equation to return to the long run relationship between the variables. Okay. This one also explained in the last recorded video. Okay, I hope you have already listened and understand. So I also updated the lab session 9. So there's one question about the ECM as well. Okay. So today we're going to discuss another topic, the one we call as the simultaneous equation model. So when we have more than one regression equation and how to explain. So this one I just realized that I didn't provide or didn't share the notes earlier. So just this afternoon I just realized that I didn't share it. So next time, so to remind me now, if you notice that I haven't shared the notes material one day earlier, for example, just let me know. So pay attention, so this is important topic. Alright, so simultaneous equation model. So all the regression model we have considered so far have been single equation regression model, in that a single dependent variable y was expressed as a function of one or more explanatory variables, the x variables. The underlying economic theory determined y dependent variable was treated as a dependent variable and x as determining causal variable. So in other words, in such single equation regression model, the causality if any ran from x to y, okay, from the regressor to the dependent variable only. So however, there are situations in which such a unidirectional relationship between y and the x variables cannot be maintained. it is quite possible that the x not only affect y, but that y can also affect one or more the independent variables. So mean that the independent variable influence the dependent variable also influence the independent variable. So if that is the case, we have a bilateral or feedback relationship between y and x. Okay. Obviously, if this is the case, the single equation modeling strategy will not suffice, and in some cases, it may be quite inappropriate because it may lead to biased result. To take into account the bilateral relationship between y and the x variables, we will therefore need more than one regression equation. Okay. Regression model in which there is more than one equation and in which they are feedback relationship among variables are known as simultaneous equation or regression model. So consider, for example, the Keynesian model of income determination. So let CT stand for consumption as expenditure, consumption expenditure, YT for income, YT represent income, and IT for investment and expenditure. So we have two equations here. So in the first equation, our dependent variable is the consumption, and then the dependent variable income. So income influence consumption. Okay, so the first equation consumption function. Second equation we have income identity. Identity means that the sum of variables are exactly the same to the dependent variable, so that's what we call identity. So we don't have any other term here. Okay. Second equation, yt equal to, the income y is equal to consumption plus investment. Okay, so the above model assume a closed economy, that is, there is no foreign trade and no government expenditure. Recall that income identity is generally written as this, which is what we call the income equal to consumption plus investment plus the government expenditure as well as and plus the foreign the trade, the next export. So the model also assumes that the investment I expenditure is determined exogenously, say by private sector. So now we can see the feedback between consumption and income. So in the first equation we have the income influence consumption. Second equation we see that the consumption influence income. Okay, this is what we call as feedback between the two variables. For simultaneous relationship between consumption, expenditure, and income. From equation 1, we can see that income affects consumption and expenditure, but from equation 2, we also see that consumption is a component of income. Thus, consumption, expenditure, and income are interdependent. So the objective of analysis is to find out how consumption, expenditure, and income are determined simultaneously. Thus, consumption and income jointly dependent variable. So the first equation, consumption dependent variable. Second equation, income independent variable are dependent variable. So they are consumption and income jointly dependent variables. Regression model in which there is more than one equation and in which there are feedback relationship among variables are known as simultaneous equation regression model. So in the language of simultaneous equation modeling, such jointly dependent variable are known as endogenous variable. Okay, so dependent variable, the variable that represent as dependent variable, we call it endogenous variable. So in the simple Keynesian model given above, investment I is not an endogenous variable, for its value is determined independently, so it is called an exogenous or predetermined variable. In general, an endogenous variable is a variable that is an inherent part of the system being studied and that is determined within the system. In other words, a variable that is caused by other variable in the causal system. So that's the endogenous. An endogenous variable is a variable entering from and determining from outside the system being studied. Okay. If they are more endogenous variable, there will be more equation, one for each of the endogenous variable. So let's say you have another variable, and then for example another variable, and then that variable can also act as dependent variable, which is influenced by consumption. For example, then you have another equation, so you have the equation more than two. Possible that you can have more than two simultaneous equation. Right, so the simultaneous equation bias inconsistency of ordinary square estimator, so the technique that we used before. So why is simultaneity a problem? Return to the first example and assume for the moment that we neglect the simultaneity between the consumption, expenditure, income, and just estimate the consumption function given by equation 1 by the usual ordinary square or as procedure. It can be shown that in the present of the simultaneity problem, the ordinary square estimator are generally not best linear unbiased estimator. So the estimate beta 1 hat is not a best linear unbiased estimator for the true value of beta 1. So beta 1 hat is a, so estimate we put hat, is a biased estimator of the true value of beta 1. On average, it underestimate or overestimate the true value of the parameter, okay, beta 1. So meaning that you use OFS to estimate simultaneous equation, then you have bias estimate of the estimate of the parameter. Okay, so bias means that the average of all possible estimate will not be equal to the true value of parameter. Okay. So one of the assumptions of the classical linear regression model is that the stochastic error term ut and the exponential variables are not correlated. Thus, in the Keynesian assumption function yt income, yt that's the income, and error term ut must not be correlated. If we want to use non-linear square to estimate the parameters of the consumption function that given by equation 1, but that is not the case here. To see this, we substitute the CT consumption in equation 2 with component from equation 1. Okay, so you put, so you replace this with this one. So yt equal to this one. So this one, this part, you replace yt with this one. C. So instead of yt, you use ct plus it. Okay, in the first equation. Okay, so the first one replace into the second one. Okay, so this one ct equal to this one. So this one, so you put it here. Okay, so instead of ct, you use this one in order to take out the ct from the equation. So you get this, and then you rearrange. Okay, we rearrange, and then we have this one. And then this, which is equivalent to this one. So you bring this to this one. So when you do divide by this one. Okay, so we get this. So now this is an interesting feature of the equation. National income yt not only depend on investment, after we substitute this one. And then you can see that, but also on the stochastic error term. Okay, but also corrected with the ut. Okay, so remember again, if you want to use ordinary square to estimate the first equation, we need to make sure that yt should not be correlated with ut. Okay, but given that yt also determines by this based as given in equation 2, so we can see here that yt is correlated with the ut. Yt correlated depends on the ut. So it's not uncorrelated, it's correlated with the ut. So meaning that the use of ordinary square s is not suitable. Okay, to estimate the parameters in the first equation. So recall that the error term represents all kinds of influences not explicitly included in the model. The point to note is that yt and ut in the first equation are correlated, and we cannot use ordinary square to estimate the parameters of the consumption function. First equation, If we persist in using it, the estimator will be biased. Not only that, the estimators are not even consistent, and estimators are said to be an inconsistent estimator if it does not approach the true parameter value even if the sample size increase indefinitely. Okay, so consistent estimator means that as we increase the sample size, then the chance for us to get the estimate which is equal or close to the true value higher lah. Okay. So in sum, then because of the correlation between YT and the error UT, the estimator data 1 is biased in small samples as well as inconsistent in large samples. So this is just about destroy the usefulness of the least square as an estimating method in the context of simultaneous equation model. Obviously, we need to explore other estimating methods, so we have to use alternative estimation approach. So now notice an interesting feature of equation 3. Equation 3, which one? This one. Okay. It expresses YT, dependent variable, as a function of the IT investment, which is given exogenously. So because in the system equation just now, in the sequential equation, we have two endogenous variables, YT and CT. YT and CT. IT is the endogenous. It is determined outside. Okay, outside of the system. Okay, it's not related to the what we call. I mean, it's not determined by the two dependent variables CT and YT. So equation 3, after we substitute, so that there is the what we call the last equation. So such an equation will express an endogenous variable solely as a function of an exogenous variable, and the error term is known as a reduced form equation or regression. Okay. So again, what we call a reduced form, because after we substitute, then we only have endogenous variable in the equation. At the right hand side of the equation, we only have endogenous. We no longer have an exogenous. Okay, originally we have YT is what we call it. CT is the endogenous. CT endogenous. Okay, so we have to substitute. So the last equation we only have IT, which is endogenous. Okay, so this YT endogenous equal to the list of endogenous variable only. So that what we call as a reduced form regression, reduced form regression equation. So again, such an equation which expresses an endogenous variable solely as a function of an exogenous variable and the error term is known as a reduced form equation or regression. If we now substitute the component of YT from equation 2 into equation 1, then we have another reduced form. Okay, so just now we replace equation 1 into equation 2, so we get this. Okay, we also can do the same by replacing equation 2 into equation 1. So just now we put this into this. So this one we put into this, and then we rearrange. That one we get one of the reduced form equation, and then we can do the same by replacing this with this one. Okay, so if you put this CT plus IT to replace this, and then you rearrange, you get another reduced equation form or reduced equation regression for the first equation. Just now we obtain for second equation. Then if we do, you also can do the same for the first equation. You get the reduced form equation for the first equation as well. So if you do the same, you will get this one for the first equation. Okay, this one for second equation, reduced form equation for the for second equation, but this one for the first one. Okay, understand? So again, if we now substitute the component of YT from equation 2 into equation 1, and then we obtain a reduced form equation for CT, which is given by this. So it is our dependent variable, our endogenous variable CT, and then at the right hand side of the equation we only have IT, which is exogenous. Sorry, this one exogenous. Okay. Alright, so the method of indirect least square, for the reason just stated, we should not use ordinary least square to estimate the parameters of beta 1 of the consumption function in equation 1, first equation. The alternative way of estimation is given by equation 4. Okay, so because it only has the regressor dependent variable only IT, that is exogenous by assumption, so that it is uncorrelated with UT. Okay, so this one equation only have IT and IT because it's exogenous, it's not correlated with the UT. Okay, it's not correlated with UT. Then okay lah, we can use ordinary square for this one. So because in this case you cannot. If you go back to the first equation, we want to estimate this one. But just now, as given this equation, we see that YT is correlated with UT. YT is correlated with UT. So that we cannot use ordinary square to estimate beta 1. Okay, to estimate beta 1, beta 0 as well lah. Okay, so alternative way is that you convert this equation into to the reduced form equation. Okay, reduced form equation which is given by equation 4 is now. Equation 4 is one, which is given by this. So this one reduced form equation for the first equation. But in this equation, our dependent variable here, we only have IT. With IT, investment is exogenous. And exogenous is not correlated with UT, meaning that now we can use, for equation 4 now, we can use ordinary square to estimate parameters. Okay, for this equation 4, we can use ordinary square whereas, because IT is not correlated with UT. IT is an exogenous. So to show how equation 4 enable us to estimate the parameters of the original consumption function, the first equation, let us write equation 4 as is. Okay, so equation 4 is one. If we use, we write like this, so meaning that the intercept is 0 plus the slope parameter for investment A1. Okay, so if you compare to this one, A0 equal to this one. Okay, equal to this one in the reduced form equation. And then A1 equal to the coefficient. This one is the coefficient for IT investment. So IT here, so meaning that it's equal to beta 1 over 1 minus beta 1. Yeah, the coefficient for IT. So as given by this one. And then the BT here equal to this one. So the coefficient A0 and A1 are known as the reduced form coefficient because they are attached to reduced form regression equation. So what you can do here, basically you need to, in order to get estimate of beta 0, beta 1 in the original equation, okay, original equation is one, this is the original equation. We want to get estimate of this, we want to estimate beta 0, beta 1, right? But we cannot use ordinary square because YT is correlated with UT. Okay, so what we need to do, convert this equation to the corresponding reduced form equation, which is given by equation 4. Equation 4 is one for equation 1 just now. This is a reduced form for equation 1. Okay, so now if we simply regress consumption against investment IT, and then we can use the estimated coefficient to get estimate of beta 0 and beta 1 in the original equation. Okay, original equation. Okay. So this one, equation 4, we can use ordinary square because IT is not correlated with the UT. So you regress consumption against investment, and then you get the estimate now. You get estimate, and then you use the estimate to calculate the coefficient in the first equation, which is given by beta 0 and beta 1. Okay, understand? So from the given relationship between A and beta coefficient, we can show that this one I will not show. It's quite how we get this. So it's quite tedious to do. Okay, so but later when we do the lab session, I will show you how. After you estimate the reduced form equation, how to use the estimate to calculate and get the estimate for the original equation, the original coefficient in the coefficient in the original equation. Okay. So for this given example, beta, if you solve this, because we know that just now A1 equal to this, and then A2 equal to this. So beta 0, beta 1 is from the original equation. But we cannot directly estimate that because the YT connected the error term. Okay, so we have to use alternative way. So from here, if you solve this one, then you get this one. So beta 0 equal to this, beta 1 equal to this. So you can use this. So A0 and A1 from the reduced form equation. A0 and 1, if you regress this against I, so they intercept and the slope. So that from the reduced form equation, Okay, and then each of these represent estimate of this one. Equal to this one, so you can use that formula, then you get estimate. So therefore, once we estimate A0 and A1, then we can retrieve beta 0 and beta 1. The method of obtaining the estimate of the parameter of the consumption function in the first equation is known as the method of indirect least square. So because we get estimate indirectly, okay, instead of directly estimate using least square for the first equation, we transform the first equation to the equivalent or corresponding or equivalent reduced form equation first, and then we estimate the reduced form equation, regress, get estimate, and then use the estimate to calculate and get estimate of the parameters in the original equation 1. So that's what we call as indirect least square. So we get estimate indirectly by using estimate from the reduced form equation. Instead of from the original equation, we use estimate, we get estimate through the reduced form equation regression. Okay. So we obtain the estimate of the original parameters indirectly by first applying ordinary square to reduced form regression. The indirect least square estimators are consistent estimator, that is, as the sample size increases indefinitely, this estimator converts to the true population values. However, in small or finite samples, the ILS or indirect least square estimator may be biased. So in contrast, the OLS estimator are biased as well. So meaning that it's better it is better than OLS because it is. Even though for small sample, it is possible to bias, but it is consistent. So as we increase sample size, then it is the potential or the chance of getting estimate equal true value is higher as compared to OLS least square. Okay, consider example 2. Basically the same example, but now we have data. Consider the data on consumption, income, and investment for the United States. So that's annual data 1960 to 1994, which is given in billions of $1992. The data on income is simply the sum of consumption and investment expenditure. Okay, so the same equation. Okay. Following our discussion on indirect least square, we first estimate the reduced form regression and we obtain the following result. Okay, now, so we have the data. Example 2, this one. So basically the same example given by equation 1. So equation 1 is now. So we have simultaneous equation. So we want to get estimate of this. Second equation, we don't need to estimate because we don't have parameters. Okay, we basically the first equation only we want to get estimate of beta 0 and beta 1. Okay, but how we cannot, because there is feedback between C and Y, so you cannot use ordinary square directly, because y correlated will be correlated with the ut. So we have to use alternative way. Okay. That by getting estimate through the reduced form equation. Okay. So this one by as given by equation 4, reduced form equation is when we need to regress. Equation 4. We need to regress consumption against the investment instead of y. In the original equation, the only dependent variable y, not I. But if we transform this to the equivalent reduced form equation, then we have to regress c against I, as given by why we can estimate this one, because again I is endogenous. I is exogenous. Okay, so that is not correlated with u. So we can estimate, we can regress y against I using OLS. Okay, because there is no feedback between y and I. Yeah. So you have to regress, but not this one. Okay, this one between C and I. So we have to. First equation is a reduced form equation. Okay, so you have to regress C against I. Okay, so now we have the data. So we want to originally we want to measure, or we want to estimate the relationship between consumption and income. The first two lah, consumption and income. But unfortunately, we cannot directly regress consumption against income because of the feedback. Similarity between them, feedback between consumption and income. So we have to use alternative way. So we need to regress we need to estimate the reduced form equation to regress consumption against investment. So given the investment is exogenous, it's not endogenous, exogenous, then we can use an square. So you just estimate as usual, create estimate equation. So you have consumption. So now we are estimating the reduced form, equation 4. Instead of equation 1, we estimate equation 4. Investment. Okay, so you can just use the least square. So it's not already square, only square. Okay, so this represent what? Estimate for A0 lah. A0, the estimate for A1. Okay, this is a reduced form equation. The A, because we regress consumption against investment, so intercept A0, 0, A1. Okay, and then we know that A0 equal to this, A1 equal to beta 1 over 1 minus beta 1. Okay, which is given by this now. A0 equal to this. So this is from the reduced form equation. This one from reduced form equation. So A0 equal to this, A1 equal to this. So we can solve this. We get this one. So now we can use the estimated value of A0 and A1 to calculate beta 0 and beta 1. Okay. So you use that information after you estimate the reduced form equation, and you use that value to. So don't worry how to get this one. I mentioned just now, this one is quite complicated to show, but later on when we do exercise, the session, I will show you how to use that value to calculate and get estimate of the parameters of coefficient in the original equation. So using this one, and then the estimated value that we obtain from the user now, and you can solve and you get estimate of beta 0 hat, estimate of beta 0 or beta 0 hat 35.1, and then beta 1 equal to this. Using this, using the formula, this one. So these are the indirect square estimate of the parameters of the consumption function, the estimated consumption function, so that can be written as this. Okay. So so now we get estimate for the first equation. That gives us estimate for the first equation. This one. Okay. But we do not get estimate directly, but we have to get estimate indirectly. So we have to calculate. We need to do some calculation. So we estimate the reduced form equation and use the estimated value to calculate estimate. So that's why we call it indirect square. So indirect way of estimation. So the equation can be written, the fitted equation for the first equation can be expressed like this. The intercept and then it's beta 0 and beta 1. So for comparison, below is the result of ordinary square. If you simply regress C against Y, so you get different estimate, but this one is not that reliable. Okay, because the present of simultaneity just now. Okay. So if you simply regress consumption against income, you get this one, but the result not that much different for this given example. Yeah. So although the estimated marginal propensity to consume do not differ substantially, there is a difference in the estimated intercept value. So intercept quite significant, means 6.54 if you use ordinary square. But through indirect square we get 35. Okay, 35. This one 6.5. But for the slope, this one 0.85, this one 0.1, just slightly different. Okay, but it's the intercept different. There is a difference in the estimated intercept values, and we should trust the result obtained from the method of the indirect square. For we know that in the present of simultaneity problem, the ordinary square results are not only biased but are inconsistent as well. So it would seem that we can always use the method of indirect square to estimate the factors of simultaneous equation model. The question is whether we can retrieve the original structural parameters from this hidden form is estimate. Sometimes we can and sometimes we cannot. So the answer depends on the so-called identification problem. So we are not always able to get estimate of the parameter in the simultaneous equation using the indirect square or using the what we call it through the reduced form equation. Sometimes we are able, it depends on the situation. Sometimes we are able to get estimate, sometimes we cannot. Yeah. So how to know whether we are able to get estimate or not? It depends on what we call as identification problem. Okay, identification problem, as I explained in the